Hey, this is Joel Duff. Welcome back. Are you ready? Are you ready for another scientific journey where we separate evidence from inference, data from dogma, and maybe facts from flood geology? Yeah, it's the fourth episode of the Dead Sea Chronicles. This time we're taking a trip to Lake Lisan. All right. You're like, Lake Lisan? Where's Lake Lisan? Well, Lake Lisan doesn't exist today. It's a Pleistocene lake. It's the Pleistocene precursor of the Dead Sea, meaning a really ancient lake that was there before any of you and I were around to see it. Imagine you're standing on the shores of the Dead Sea today, right? Today you'd just be looking out at some really briny waters. You'd have the Jordan River coming down into it. You'd have the Sea of Galilee farther up north. But now let's picture yourself standing, well, not right on the shore of the Dead Sea, because you'd have to look way up through the water several hundred feet to see the surface. Let's say 25,000 years ago, you're standing, on the mountains around the Dead Sea and you're looking out. What would you see? Well, instead of a small shrinking lake, right, you'd be gazing across a vast body of water that would stretch pretty much as far as you could see. Right? Because there would be a lake that would stretch below the southern portion of the Dead Sea, and you'd have to look all the way up north of the Sea of Galilee, and the entire valley would be full of water. So that's what we're going to do. We're going to take a look at Lake Lisan. That's the name that's been given to this particular lake. And that's going to be our next stop on our geobiblical exploration of the Dead Sea origins. Now, before we can go on this little excursion to Lake Lisan, we got to go back a little bit further in time and look at the precursor even to that particular lake. But I want to just quickly summarize a few things we've talked about so far in this series, right? This is part 4. So in part 1, we took just a big survey of the lay of the land, all right? The Dead Sea Rift, the Jordan River, Sea of Galilee. What's the geography of this area? Then we talked about how the Dead Sea is getting lower and lower and lower, right? That the water is drying up. The water from the Jordan River has been taken away for agriculture and other things, resulting in much less water getting down to the bottom of the basin where it can't escape other than evaporation. And that's what's happening. It's evaporating, and the lake is getting lower and lower and lower. All right, that's the present reality. But then we started to get into our real question, which is, what is the origin of the Dead Sea? Where did the Dead Sea come from? And in order to understand the origin of the Dead Sea, you have to understand the origin of the valley itself. Where did this giant crack in the earth come from? And how did it get filled with the sediments that it has in it today? All right, so we have this Dead Sea, which is over 1,200 feet below sea level and getting lower. We have these sort of mountains around it, but this uplifted land around it. We spent a good amount of time talking about this fault system, about how the Jordan Valley represents 2 continental plates that are sliding past each other. And as they're doing that, they're also pulling away from one another. And the land is uplifting. And as it pulls away, the land around is uplifting, but the land between the uplift, all right, where the land is being pulled apart, is actually falling down farther and farther and farther down into the earth, like 15,000 feet down. And as it does that, we talked about how, sediments are then going to begin to accumulate in that basin from erosion. But what we didn't say was there could be a lake in there at that time, and that the sediments are actually in the lake and then falling to the bottom of the lake and piling up as the basin is falling down. But I did note in the last episode one interesting feature of this basin, and that is it's full of salt. Several thousand feet, actually around 6,000 feet of salt, and a couple thousand feet of gypsum and other precipitated minerals. And there's a whole bunch of other sediments as well, like normal sort of sediments you would have from a lake where you have, sand and silt and clays and so forth that are piling up too. So that all adds up to 15,000 feet of stuff that is now sitting below the bottom of the Dead Sea. And the question we have for us today is, where did all that salt come from? How did you get so much salt in that place? Sure, you can walk on the shores of the Dead Sea now and you can see like it's a really salty place. And along the shores, there's salt precipitating out where the water's splashing up on the edges and it dries out and salt crystals form. And it's like, yeah, there you go. Like salt is forming. And as more water gets deposited in the valley, that brings some more salt in and the water evaporates. It leaves salt behind. So you're like, okay, that's where it came from. But 6,000 feet of that, that's a whole lot of salt. All right, so maybe I understand where that salt could have come from, but how long did it take to form? That's the question we want to address. Like I said before we can visit Lake Lisan to try to help us explain that, it's not going to fully explain all those 15,000 feet of sediments below the Dead Sea. We need to go even back farther in time to the very beginnings of the rift, the beginnings of the basin, when the basin wasn't nearly as deep as it is today. So this figure kind of like sums this up for us, right? Here in 2019, we see all the features that we're used to seeing, right? Dead Sea, the southern portion of the Dead Sea is pretty much drying up and it's separated from the northern part of the Dead Sea now. That wasn't the case in 1930 when it was all one big lake. And so we see the fact that the whole area has dried up more than it was before. We got the Sea of Galilee, the Jordan Valley. Right. And as I've said in previous episodes, if we went back 4,000 years, you would have seen a Sea of Galilee. You would have had a Jordan River. You would have had a Dead Sea. Right. You would have had a valley that had springs and other things in it. Right. And even, cities, right. Villages, right. In the basin, suggesting that since 4,000 years to present, what you're seeing here in 1930 and 2019 is pretty much a picture of what you would have seen for thousands of years. In fact, all eyewitness reports we have from the Dead Sea region, from the Jordan Valley, all suggest that the climate and what you would have seen is very similar to what it is today. But we have lots of evidence, some of which I'm going to bring to you today, and some of which I'm going to cover in subsequent episodes, that I think will convince you that this valley hasn't always looked like it does today. So if you go back 14,000 years to 70,000 years, there would have been a large lake filling this valley from end to end. And that lake went up and down. Sometimes it was connected to the Sea of Galilee. Sometimes it got reduced and there was something like the Dead Sea, but a little bit larger than the Dead Sea. And then it grew and then it got smaller. We'll look at a little bit of the evidence for that. But as I said before, we actually have to go back a little farther in time first to begin this story. All right. And the story is about where did the salt deposits in the Dead Sea come from? Geologists studying the Dead Sea region have developed a really detailed understanding of the complex history. They've divided the evolution of the Dead Sea Valley Rift, or the Dead Sea Transform, as we called it last time, into several distinct stages that you're seeing here. And this history extends like way beyond, way deeper than Lake Lisan, which is what we'd call the immediate precursor before the modern Dead Sea. The early stages of the rift began, 20 million years ago. So that's when the rift starts to open up as the Arabian Plateau separates from the African plate. So initially the rift formed a valley that maintained a connection once in a while to the Mediterranean Sea. We think this Mediterranean Sea connection might have persisted for 3 to 5 million years. And during that time, what would have happened? Well, water from the Mediterranean would have flowed intermittently or continuously into the Jordan Valley as the sea level is fluctuating in the Mediterranean Sea. You remember, sea levels are not always constant, right? Especially if there's ice ages, the water would have been lower, breaks the connection, raises up, maybe creates a connection between this valley and so forth. So as global climate changes happen, you have interruptions in this process of transferring water from the Mediterranean Sea to the Dead Sea Valley. Well, if you're getting water from the Mediterranean Sea is quite salty, as I'm going to show you in a little bit here. And so you're feeding salt water into what they call this lagoon system, the Sedum Lagoon. This would have all been a fairly shallow area, a very shallow basin at the time. So any water that's there is going to evaporate a lot. And as it evaporates, of course, it becomes even saltier. And that's what's going to lead to salt production. So during this period, known as the Sedum Lagoon stage, this really huge, enormous hypersaline water body formed. And there was continuous evaporation in an arid climate, and therefore the water became supersaturated with salt. And that's what begins to form what's called the sediment formation, which is this really thick sequence of evaporites that deposited during this time. So we're talking about millions of years of constant evaporation in this region, resulting in every year a little bit of new salts, new precipitates actually falling to the bottom of this lagoon and piling up. There's been studies, and again, I'm gonna point you to my blog post that's related to this particular episode, which is going to have like all the references and additional details about these things. Right? So what's happening is you're going to say like, well, how would you get 6,000 feet of salt if it's very shallow? Right? If it's very shallow and the salt piles up, eventually it's going to be at sea level, in which case, how can you add more salt on top of that? But what's happening is in the rift, remember, the rift is pulling apart very gradually over time. We looked at 4 or 5 millimeters per year. Well, that's the motion, but it's also pulling apart probably even by fewer than that. So maybe a couple millimeters per year. But as it does so, once in a while, the whole thing is dropping down a little bit. So it's also going down a few millimeters a year. And as a result, that constantly makes more room for more salt, right? Salt deposits. It gets up close to sea level. It's very, very shallow, but then the basin's still falling. And as it falls, well, then there's more room for salt water, which is evaporating and then laying down more salt. And then it continues to fall, right? So it's like a conveyor belt. Like the land just keeps lowering and the salt just keeps going up, right? The land goes down and the salt comes up. And it just keeps doing that, right? For long, long, long periods of time. You see, if it was really deep, it would never get salty enough to have that much precipitation happen, right? You have to get really dense. Like the Dead Sea today, even though it's 350 parts per thousand salt, which is extremely salty, actually is only just at the edge of getting salty enough to deposit actual salt in the bottom of the Dead Sea. Yes, it gets deposited around the edges, but it isn't necessarily creating a lot of salt precipitation that falls out in the lake itself. But if you have a shallow basin, a shallow sea, right, you can get to extreme levels of saltiness, which then actually create precipitation. So in order to keep thousands of feet of salt, you have to keep this constant conveyor belt going of constant salt production over and over and over again. Now, what people who study this region, and we'll see how they study that and like how did they come to these conclusions? Are you just making this up, or is there actual evidence to back this up? Now, let me tell the story first, and then I'll start feeding you some data, which again is going to occur over the next couple episodes. After this period of time of the lagoon, eventually the marine water source is cut off, right? And then there's a very arid environment. And so what happens at that time is the water starts to dry up, all right? But the basin is still falling. And as the basin falls, then this whole area starts to go below sea level. And then a very large lake forms called Lake Amora, right? And Lake Amora was a much larger lake than even Lake Lisan would have been. And during that time period, we're going to see that the layers of sediment that are laid down aren't necessarily like salts and gypsums, that they actually have a lot of other sediments in them. That's because it's a basin now. Well, when it's a basin, you have erosion. Erosion brings in fine particles, and those fine particles begin to settle to the bottom of that lake. And that forms lots of layers of things, right? Right? Not just salt crystals. And it wasn't as salty, so it's not forming as much halite. So that particular lake forms because there is a basin now and water's filling that basin. And when it's like, well, how could it fill that basin if it was really dry? Well, the climate was very likely not as dry. In fact, that's one of the evidences that this area was much, much wetter at that time because it could support a large lake. And same thing with Lake Lisan. The basin's no bigger during the time of Lake Lisan as it is today. So the fact that there was a very large lake there means what? It means there must have been a lot more rain. There must have been a lot more rain, a lot more snow, a lot more water being fed into the basin in order to maintain that lake. And temperatures had to be cooler, all right, in order to prevent as much evaporation. And so that gives you the water balance, which increases the height of the lake. Today, it's just extremely dry and arid, and there's lots of evaporation and not much water coming in, which is why it's going down. So let me show you some actual papers to illustrate some of these points that I just made. So here we have an article from the journal Clay Minerals. Yes, a whole journal dedicated to clay minerals from 2009. Climatic changes during the Pliocene, which is the early time period we're talking about here, more than 70,000 years ago. This is millions of years. As observed from climate-sensitive rocks and clay minerals of the sediment formation of the Dead Sea Basin. And so here we have, and the reason I'm bringing this one up because we have a couple of figures here, right? It's saying, look, here's a cross section right down here at this sort of down here at the bottom of the Dead Sea, the lower portion of the Dead Sea. And so there, what you have is you see these little triangles. I don't know how obvious this is going to be to you, but all these little triangles represent salt deposit. That's halite, like rock salt. And so from all the way from the bottom of this section, which is 500, 800, 1300. Yeah, this is like more than 10,000 feet below the bottom of the basin. All right. So 11 or 12,000 feet below sea level. You have thousands and thousands and thousands of feet of salt. You also have anhydrite and gypsum. That's the other symbol that's in here. And then you have a whole section where there's mostly anhydrite and gypsum, which is extreme desiccation. And then eventually closer to the top, you have marls and conglomerates and chalks and so forth, right? Chalk represents like there's actually maybe living organisms that are present, and the little tiny bodies from those are being accumulated at the bottom of the floor. Well, you know what? There's not a lot of living things in the Dead Sea today because it's too salty. That's a nice little piece of evidence that the lake that was present at that time wasn't as salty, right? There were actually other organisms living in the lake. And their remains are now found in the sediments, at the bottom of that particular lake. And then look at this. There's a little layer where there's just a bunch of salt. And that might suggest that the lake had dried up quite a bit, got salty enough that salt could precipitate, form a layer of salt. This happens multiple times. And today, by the way, when we're talking about today's sediments, here's the Holocene up here, the last 10,000 years. The last 10,000 years is just this little tiny bit of stuff at the very top of this huge column of sediments that sit below the Jordan Valley. Right? So this gives you an idea of the enormity of the problem. And in a later episode, we're going to look at just the first 40 meters. All right, a very small portion of a column that's been drilled down into the bottom of the Dead Sea. And we will see evidence. I'm going to show you evidence which we can tie to 2,000 years ago and events that happened like around the time of Christ, which is only like, I think, 18 meters below the sea, below the bottom of the sea. Right, so all of recent history is captured in the very top piece of this sedimentary column. And we have thousands of feet. And just a reminder, what is below all of this? What's below that is another 15,000 feet of Miocene rock, which is just 30 million years old and older. Then you've got all your rocks from the age of the dinosaurs. All right. And then you have your even older rocks below that, right? You have huge amounts of fossil bearing rocks that are below this whole thing. And so all of this salt sits on top of the older rocks of the geological column. And then here's another illustration of this lagoon that would have been created when there was a connection with the Mediterranean Sea. And so waters from the Mediterranean Sea come in here. See, here's how the conveyor belt works, right? Water comes in and it comes into a shallow area in a hot, dry climate. The water evaporates. As it evaporates, where is it going to get more water? Oh, well, maybe from the Mediterranean Sea. In other words, the water is just constantly flowing in here because it's evaporating out, flowing in, evaporating out, flowing in, evaporating out. So that means you have really salty water coming in. Then it gets evaporated. The water gets evaporated. The salts get stuck behind and they fall to the bottom of that lake, or in this case, the swamps, basically, the lagoon, right? And they pile up there. And as long as you have this connection with the Mediterranean Sea, you can generate an enormous amount of salt production, right? Now, enormous still means, you're only laying down like, I'm laying down an inch or two potentially of salt in a year. I'd say most of the time, not that much, but, potentially you could actually get a pretty good salt out of that. But remember, we're going to talk about 6,000 feet of salt. So we're talking about, even if it was a maximum salt production every year, all the time, just constantly loading salt. We're still talking about 50 to 70,000 years in order to lay all that salt down. That would be an extremely high rate of salt production, a very unrealistic salt production rate. Okay, I tossed this particular map back in because I wanted to show you again, I emphasize that, here we have our deep valley and we still have the scar left over. All right, we still have this little area, this valley actually, that runs over to the Mediterranean Sea right here where Mount Carmel is. And although this is still hundreds of feet above sea level at this place, we also know that there's been some uplift. Oh, what caused the Mediterranean Sea to lose its connection with the Jordan Valley? Well, we know that we think that we have uplift of this region, right? Creating the higher mountains that we see today. That uplift eventually would have cut off the connection of this valley with the Mediterranean Sea. And if you look at the sediments that are in this valley and you drill down in there, what you'll find is you have like marine type sediments and you have a lot of salts and other things that suggest that this was a marine corridor at one time going over to the Dead Sea Valley. Okay, so this would have been a long time ago, but occurring over long periods of time. Not always being connected to the Mediterranean Sea, but maybe it was connected, disconnected, maybe it's connected, disconnected. And that's why it would have taken so long also to collect 6,000 feet of salt, is that maybe for tens of thousands of years, you kind of got the conveyor belt going. Then you have a disconnection. Maybe the whole thing dries up. You're not going to have any salt production then, right? And then, maybe a few thousand years later, right, the oceans rise a little bit, the connection is remade, the water starts to flow in, you get salt again, you start having salt production again, right? If that's occurring, 10,000 years on, 10,000 years off, well, then it's going to take a long time to pile up 6,000 feet of salt. And by the way, the 6,000 feet of salt is not, when we look at Mount Sedum, and I show you pictures of that, it's not like just like pure salt. It's like, blocks of salt, and then you have small little layers of sediments, right? Other things that are between the salt layers. Well, that would represent, hey, I have thousands of years of salt production, but then all of a sudden I had now I had like only fresh water coming in, and I had some sediments in there because I didn't have the connection to the Mediterranean Sea, right? The environment changed. And then, the Mediterranean Sea got connected again, and now the salt production begins again, right? So I lay some layers of salt down, right? So you have these changes in the climate represented in the different layers that are below the Dead Sea today. I mean, you can see that in this image over here, right? It's not everything is completely uniform. There are specific groups, names of different layers of sediment that must represent different climatic conditions from the past. All right. So one of the reasons we know about this is because there's a drill core that's been taken in the Dead Sea, all down through the bottom of the Dead Sea, all the way down more than 15,000 feet below, and pulled up. And so we can see all these different layers. So we've gone all the way down into the Miocene rock. And that's how we know there's a huge section of other sediments that are basin fill on top of the original Miocene rock, which wouldn't have formed in this basin. It would have formed when it was like near the surface. Okay, so one other little thing here, I think this is just interesting, and it, in case you're wondering about the salt production. All right, this is just a map of sea surface salinity, which is good enough. I mean, that's the amount of salt in the water at the surface. Below the surface, it can vary quite a bit, all right, between deep ocean, mid-ocean, and so forth. But at the sea surface, where you have evaporation occurring, you can have local regions with fairly high salt production. So it's not surprising that in the middle of the Atlantic, around the equator, you have high salinity ocean water because you have a lot of evaporation occurring, and that's creating higher concentrations of salt at the surface. If you go to the Mediterranean Sea, you see how dark this is in the Mediterranean Sea? 38, 39 parts per thousand salt compared to out here where you have anywhere from, down to 31 up to 36, right? That's only 2 parts per million more, but that's actually a fairly significant amount of additional salt. So the Mediterranean Sea has 39, and there's actually a gradation between the opening of the Mediterranean Sea where it's connected to Atlantic. By the way, Atlantic waters run into the generally move into the Mediterranean Sea, because what's happening in the Mediterranean Sea is a lot of evaporation, and because water is evaporating out, then you're concentrating the salts. All right. And so as you get farther, farther, farther over toward the Middle East, you end up with the most concentrated salts in the Mediterranean Sea are along the coast of Israel and Lebanon and Turkey. And there you have 39 and above parts per thousand. You might think, well, that's a lot of salt. That's pretty salt. Remember, the Dead Sea is 350, right? 9 times as salty as the Mediterranean water. But it's thought that the Mediterranean Sea was kind of similar, 5 million years ago. And well, actually 5 million years ago, the Dead Sea was probably dried. The Mediterranean Sea was probably dried up. Oh, that's another story for another time. I'm going to do a whole episode on that later. That's after the 12-part series. Okay. We're going to talk about the Mediterranean Sea and it drying up completely and leaving a giant amount of salt at the bottom of the Mediterranean Sea, which like far exceeds even what we see in the Dead Sea. But anyway, the point is that a lot of salt here in this water would have then moved into the lagoon. And so it started out with even pretty salty water, and then more evaporation brought it to 350 to maybe 400 parts per thousand. At that point, you then have salt, just like salt crystals forming and falling to the bottom of the lagoon. So now we got to move into talking about Lake Lisan, right? The floor of the Jordan Valley is subsiding. It keeps on going down. It's cut off from the Mediterranean Sea. So like 70,000 years ago, the whole valley is continuing to drop. The environment is more arid. I'm going to show you evidence of that in a moment. Actually, in this paper provides some evidence of that. And as it falls, the lake is starting to recede. It's still filling a portion of the valley, but it's below sea level. And that's when we get what is called Lake Lisan. And it really is a giant lake. That lake at one time was, as much as only 500 feet below sea level. Now, remember, it's 1,400 feet below sea level today. I said 1,200 earlier. It's actually all the way down to 1,400 feet below sea level. So 500 feet below sea level, well, that's still 900 feet higher than it is today. Now, if you add 900 feet of water on top of the Dead Sea, guess what? You're going to be a lake that's going to go all the way up to the Sea of Galilee. The Sea of Galilee is 700 feet below sea level. So when this lake was 500 feet below sea level, it was 200 feet above where the Sea of Galilee is today. And really, by 70,000 years, the whole basin has fallen so far that it's kind of similar to what it is today. So it wasn't just deeper, it was just a much more extensive lake. So how do we know that there were large lakes in the Jordan Valley in the past? There's a bunch of different pretty obvious evidences that there was a larger lake. One of them is that we have wave-cut platforms along the edges of the Dead Sea Basin, running all the way from the Sea of Galilee down to the Dead Sea. If you look up on the sides of the hills there, right, you'll see wave-cut basins. So a wave-cut basin is if you have a lake and it stays at a similar level for a while, what happens is the lake shore laps up against the side of the side of a valley, the side of the valley, right? And as it does so, it basically cuts into the side of that valley and creates a beach. And then when the lake recedes, it leaves that beach high and dry. And that's what we see. We see beaches, all levels of beaches. Now, the next episode is going to be about identifying those beaches and dating the ages of different beaches at different levels. And that's one of the ways we figure out the sea was here, and then it was here, and then it came down here, and then it went all the way back up here again. And so we measure the changes or the fluctuations in Lake Lisan that way. All right, that's one way of doing it. But there's another thing. There's also the presence of aragonite deposits along ancient shorelines. Right, that's a form of calcium carbonate, and that precipitates out of water under certain conditions. The presence of these deposits tells us that the chemistry of the ancient lake, and it provides minerals that can be dated using uranium-thorium methods. That's a form of radioactive dating. And because of this particular mineral that precipitates only under these conditions, which is basically near the shoreline of a lake, all right, in which the lake is fairly saline, all right, it's a not hypersaline lake. Because it's larger, it has a larger amount of water and more water flow into it. It's not as dense. And so certain kinds of chemicals are precipitating along the shores, and we're going to look at stromatolites in the next episode as well. And we see from that that tells us about the water chemistry of a lake that was present at that point in time. There's another thing that happens too, is you get precipitates. Well, you get sedimentation, right? You have things coming into the lake, right? You have streams coming into the lake. They're bringing sediments. The sediments are falling to the bottom of that lake. Well, now what happens if the Lake Lisan is only 500 feet below sea level and it's going from the Sea of Galilee all the way down the Dead Sea? Well, that means lots of places where today are above sea level or above the lake level, right? There must be covered with sediments from that previous lake. And sure enough, we have huge piles, sometimes 100 feet or more, of sediments that have varves in them. All right. Varves would be little individual couplets that look like rainy season, dry season, rainy season, dry season, rainy season, dry season. You see, during the dry season, you have a lot of evaporation. You end up getting stuff precipitating, falling to the bottom. Rainy season, you have a lot of sediments flowing in from temporary streams, bringing sediment into the lake, and then the sediments fall to the bottom of the lake. And so you get these patterns of rain, dry, rain, dry, rain, dry, rain, dry, rain, dry, which pretty much represent annual rings. And there's tens of thousands of annual rings in these columns of sediment. I'm getting ahead of myself. I've got pictures. I should be showing you pictures while I'm talking. So this is a picture of Lake Lisan, 25,000 years ago, and the extent of it. Now remember, the basin edge is basically the same 25,000 years ago as it is today. So this is the extent to which all water from inside of this white line would flow into the basin. So if you have a large lake there, it tells you there was more, well, two things were happening. Probably wasn't as hot and dry as it is today, and there was more vegetation. Well, if it wasn't as hot and dry and there was more liquid in the environment, right, more rain, there's probably going to be more vegetation. And we have evidence of that vegetation that comes from this paper, right? Dead Sea pollen record. Because what's happening in this lake, as this lake is dropping sediment to the bottom of this lake and piling up on the bottom, what today is the Jordan Valley, we can go to the Jordan Valley and go down and look through those sediments, right? Which is a history of this lake. And we can look at those layers, which especially if they're annual rings. And we can say, we'll just pull out the pollen, right? And if you pull out the pollen from different layers and look at it over time, you can see how, oh, look, when the lake was really high, giving away the story here, when the lake was very high, we have lots of pollen from lots of different plants that don't typically grow in this really arid environment. And then when we see that the layers, then when we see evidence that the lake was much, much lower, in other words, you start to see salt deposits and other things when it gets to be a hypersaline lake, meaning that the lake is much lower level, then we start seeing pollen from plants from an arid environment, right? Pollen's awesome. Pollen's a great, a chronology keeper, right? It tells us about climate change. So what would make the climate change? Well, you have ice ages, right? You have a couple ice ages happening from 70,000 to 14,000 years ago. You have changes in Europe occurring. Now, how would that change this particular region? Well, if you change the ocean water from the Mediterranean and change the temperature of that changes the airflow patterns and so forth. So sometimes you had water coming in from over the Mediterranean. Other times you have air patterns the other direction. Lots of modeling has been done to show how the climate would have changed in the past. And then, of course, what it might change to in the future as well. All right. And this is what I'm not going to go over the details of this particular figure. I just want to show you what a pollen profile looks like. And this very top part, actually, unfortunately, this is, the last couple thousand years is just in this little tiny sliver at the very top. And so you can't really see the full impact of the fact that it's much more of a desert today than it was in the past. But analysis of the different pine pollens and different deciduous trees and grasses and all these different things that are in the pollen record, then allow us to map over time as you go down the core, and here's the age, right? 20,000 years, 30,000 years, 40,000 years, 50,000 years, 60,000 years, right? As you move down your core, as you move down the sediment profile, you're going deeper and deeper in time, and you're pulling out the pollen from those times. We see what doesn't I admit on this chart doesn't look like drastic changes, although there are a few things that changed a lot, like the amount of charcoal. Interesting measure, right? You can look at charcoal found in that. So if there's large fires that throw up ash into the air, well, the ash falls into the lake, falls to the bottom of the lake, eventually makes its way down to the bottom of the lake and gets trapped in layers. And so charcoal is something that would tell you that there was a lot of vegetation, but there's also dry seasons. And so you have a lot more burning occurring at some times in history than others. Many, many, many studies have been done looking at cores through sediments and looking at changes in the types of plants that are in the region around it. Because after all, where does the pollen come from that's in this lake? It must come from the plants that are in this local region. And so you can learn a lot about the past history. So now then we bring us to this really important paper. I mentioned this paper multiple times in my write-up on this by Adi Torfstein and colleagues. This is published in Geochimica et Cosmochimica, ACTA, and in 2013. Integrated multi-site uranium-thorium chronology, and they're looking at different stages on of the shorelines and dating when the lake was at different stages, at different lake levels in the past. So again, here's their figure of the Dead Sea, and they're pointing out that they're taking measurements from different sites around the Dead Sea where there's thick layers of sediment. This is the deepest portion of the Dead Sea Basin. So when there was a lake, this would have been the deepest section of it. And so it receives, a good amount of sediments and so forth. And so they're saying, in the past, this whole thing was a lake, in which case all these flights where we're sampling were underneath the water. And so here are some examples of what that looks like. And here you have, and this is in meters, so 30 meters, you think of that as 90 to 100 feet, right? So here's 100 feet. And here's all these different layers, and you see there's different colors in here. So you have silts and shales and so forth. That represents different sediment sizes, different chemical composition of the water that affects the types of things that the minerals that are forming, right? And so that suggests that the water of the lake that was above all of this was changing over time. The inputs of what's coming into the lake are different at different time periods. And here we have another location, and there's I'm not showing you up close. There's very minute, very, very, very thin bands that represent hundreds, thousands. In this case, I think in one of these areas, I think it might be in this White Cliff at Masada. You notice Masada? These are cliffs that are right along the edges of Masada. So Masada itself has piles of sediments around it that are represented by Lake Lisan sediments, right? Sediments that are lake sediments. And there are tens of thousands of individual couplets, which are usually interpreted as annual rings. So tens of thousands of years of sediment deposition, this being at the bottom of a lake at that time. And again, here we have a bunch of stuff. Here they're actually noting there's a beach bar right here, meaning that at some point the lake was at such a level that, it was above all this, laying down sediments, and then maybe the lake level came down. And when it came down, you ended up with sediments from the beach sediments forming there, right? Maybe there's a stream that comes in there, brings sort of like, larger sediment size stuff. And there's also wave action happening here. So it disrupts that. And then maybe the lake rose. Well, obviously it must have, right? The lake went way higher again. So all this area was underneath the water, and then sediments just raining out and then falling in nice, perfectly aligned layers. And these layers aren't very disturbed, right? They don't have turbidites. Turbidites are where little animals and critters are at the bottom of the lake or climbing around, or fish are swimming by and they're disturbing the sediments on the bottom of the lake, right? That disturbs all the sediments, right? Mixes them up. Like if there's worms in there and they're moving around, digging in the material, it's going to ruin the thin lines. But because this thing was pretty salty, right? There's not a lot of organisms in Lake Lisan. Lake Lisan was probably a lot similar to the Dead Sea in terms of being pretty dead. There's not a lot of fossils in this. right? There aren't any large organisms that I know of that are fossilized in like this Masada complex here. That suggests a deadish lake that then has undisturbed bottom surface. And that's wonderful because then we get to see fine scale changes over time because they don't get disturbed. All right, so what does Torstein able to do then? They're able to take these different dates of these different layers and infer how big the lake was at that time. All right. Part of that's from the water chemistry, from the chemistry of the rocks themselves. It tells it like this lake must have been much larger, not as salty. And other times it's saltier, it's probably lower, generally. Then they're looking at the wave cut benches along the shores and they're dating those. And they're like, look, the lake was at this level at this particular time period. And so this is where you get this map here where you have, here's lake level elevation, so that's below mean sea level. All right, so 160 meters down to 420 meters, right? It's 423 meters below sea level today. That's 1,400 some feet below sea level. This was published in 2013, so they didn't know, like, we don't have like, this line goes down all the way down here, right? And so over the last, it's down here where the scale is, 5,000 years. Okay, that brings us pretty close to talking about the young Earth creationist angle, which we're going to get to in a minute. Over the last 5,000 years, not a lot of drama, right? It's going to up and down, up and down, up and down, like 20, 30, 40 feet here and there. But what I've been saying is that even if you go back to 4,000 years ago or 5,000 years ago, and you said like, Lot and Abraham are looking out over this basin and they're checking it out, right? 4,000 years ago. The lake level's not that different. There is a Dead Sea and there's a Sea of Galilee. There's a Jordan River, right? But you keep cruising back in time, right? So this is all, from like basically the Ice Age, the end of the Ice Age here, all the way to the present. Kind of boring. It's a dry, arid environment. But you hit like 14,000 years ago, and all of a sudden, the lake level, there's a lot of evidence that, boom, this thing's all the way up here, 100 meters, 300 feet higher. When you get 300 feet higher, you're connecting the Dead Sea to the Sea of Galilee. There's no Jordan River between those two at that time. And then you get back to 25,000 years ago, it's only 160 feet below sea level. I'm sorry, 160 meters below sea level. So, 450 feet below sea level. That's 1,000 feet higher than it is today. Add 1,000 feet to the bottom of the Dead Sea Basin. It wouldn't look like it does today. And how could it possibly be that high? Because it's the same basin in terms of surface area, square footage of area to bring water into it. Boy, that wasn't a very efficient way of saying that. So it had to have been a wetter environment. There just had to have been a lot more water in the environment, a lot more rain, right? And lower evaporation. And so the water levels go up. Now it takes several thousand years for this to occur, right? And actually moving forward, it's dropping quite rapidly from 25,000 years ago all the way down to 10,000 years ago. It loses 8,000 feet over that period of time. And then if you go back from that 30,000 years, 40,000 years, 50,000 years, 60,000, you see it's like, it was down lower, then it was up higher, then it was down lower, then it was up higher, and then down lower and up higher and so forth. After you get to 70,000 years and you go back from that, it actually goes up again. And then you have Lake Amora, and that's a larger lake. And then, of course, much farther back in time, it's up near like sea level. All right. But this 70,000 to 14,000 year period is a period of a lower lake, but much higher than today, which is why we give it a different name, Lake Lisan. Right. And during that time, there's deposition of different types of rock. Actually, there's very little halite production, salt production during this time. Right. You have salt today because it's hypersaline. But when it's much higher, it's not as hypersaline. This is just different kinds of sediments. Actually, I think 5, this is, what is 5? 5 is anhydrite, aragonite detritus. Oh, aragonite detritus couplets. So that this it's during this stage, during these several tens of thousands of years, in which you have mostly aragonite detritus couplets. So aragonite is the mineral precipitation that occurs when it's the dry season. And then during the rainy season, you get detritus and other stuff from you get pollen, you get plant material that's washed in, right? You get other sediments, right? And you get that couplet. So it goes back and forth. And there's whole large sections of this where it's just couplet after couplet after couplet. Then you do have a few places where you end up with gypsum and halite. And that would represent times in which the water got, it got much more dense. As the water's falling, much more evaporation is occurring. You had periods where you had halite production. Okay, so that's the fluctuating Lake Lisan Lake, right? Represents 70,000 to 14,000 years ago. These are Lake Lisan. All of this material is Lake Lisan deposits. This is the Dead Sea here, right? And so this region here is the Lake Lisan peninsula that actually sticks out into the Dead Sea. It's actually being pushed up somewhat. It's being pushed up because there is a giant salt diapir between it. So there's a massive amount of salt below this from the lagoon salts, which were thousands of feet of salt, right? Not hundreds of feet of sediments from Lake Lisan. That's why I'm saying Lake Lisan doesn't solve the problem of where all the salt came from. Because when there was a large, deep lake there, you didn't get salt production. You just had couplets, which over tens of thousands of years still only stacked up to, 100 feet or 200 feet. Right? It's not that much compared to 15,000 feet of total amounts of sediments in the basin. But anyway, this particular area is being pushed up by all the salt below. And so it's actually being raised up higher, even as the basin is falling. And so some of this was actually probably a little bit lower and it's been lifted out of the Dead Sea. But all these sediments here, this is where you can look at the layers and actually count up those couplets and so forth. All right, a couple other things. Here's a paper from 2000. And I just want to show, here's a formation from before Lake Lisan. So these are older deposits from Lake Moran. And then you have an unconformity. An unconformity would be you had deposits from a large lake. That large lake then dried up. And then after it dried up, you had erosion of the surface. And then the lake rose again to form Lake Lisan. So there were periods in the past before Lake Lisan, after more, in which the water levels went way up and way down. Not going to show you those. I mean, there's lots of different sections of history that people have studied. And so that's called an unconformity because you don't have this isn't continual deposition. This is deposition, very slowly over time because each one of these little thin layers in here represent years or decades or even thousands of years. That's all piling up slowly underneath a big lake. Then you had disruption of that, meaning the lake doesn't exist. And there's erosion of some of the surface. And then the lake rises again. And then now it's under the lake. And now you have many, many, many thin layers of rock being laid down. All right. So now we come to the biggie, right? The big question. We've spent a lot of time just giving you an idea of the enormity of the problem, really. And I haven't shown you a lot of data, but I think that just showing you the total amounts of salt that are there should get you thinking, like, how would that occur? We are going to do a calculation later. I have a whole episode in which we're just going to be doing calculations of a potential model for young Earth creationists, which is, what if this whole thing was a giant lake in the past and then it was salty? And what if the whole thing dried up over a period of like a couple hundred years? How much salt would that leave? Because maybe it would just like leave a whole big giant chunk of salt below the current sea, and that might explain everything. I don't think it's going to take you much imagination to realize that that is not going to solve the problem. But I'm going to do the calculation for you. We're going to ask, like, if you took 3,000 feet of water, of salt water, and you dried it all up, how much salt would you be left with? Right? That's my teaser, right, for a future episode. But now let's just hit some highlights for how does this fit into a young Earth creationist chronology? All right, I'll give you the answer. It doesn't. It just, this is why I'm doing this whole series. This to me is one of the most profound, provocative examples of an impossibility for young earth creationists. I just don't know how they squeeze all of these events into a 4,500 year history. And really, it's not 4,500 years. I've been using this example, and I'm going to say it in every episode. I'm using this particular place as an example of evidence of an ancient earth because we have eyewitness reports from scriptures that this place didn't look that different 4,000 years ago. All right. And the water couldn't have been higher after 4,000 years. Like you could say, well, maybe 3,000 years ago, Lake Lisan was there. Nah, couldn't be. Because if it was, we'd have sediments covering lots of different cities. Like, how about Jericho? Jericho would have been hundreds of feet underneath the water if Lake Lisan had existed after Abraham and Lot saw this valley. There's no evidence of sediments ever having, a lake having covered the Jericho. All right, so that's the thing is we have eyewitness records throughout the last 4,000 years that tell us there was no giant lake here. All right, so that compresses all of these observations you have to explain within an extremely short period of time. All right, so let's just go through some of them. I'll try to do this fairly quickly because I know we're running kind of long here. So what are some of the challenges? I'll just list some of the challenges we've seen so far in the series, and then we're going to do this again later when I do one big summary in one of the last episodes of this series. Well, we got a time frame issue. Lake Lisan, from calculations based on uranium-thorium dating, and then just straightforward counting of couplets, if they're annual rings, varves, suggests that there are tens of thousands of years involved in the production of those. So we think that this lake existed for about 56,000 years as sort of in this, like between this level and this level, right? That's sort of the definition of Lake Lisan. 70,000 years to 14,000 years ago. And then since then, it's just been dropping, right? That time frame alone, where does that fit in the 6,000-year-old Earth? The annual layers, right? We have thousands of varves that are hundreds of feet above the Dead Sea. Above the sea, above the Dead Sea, on the sides of the mountains where there's been deposition from previous lakes, there are thousands of little layers that we interpret as being annual deposits. All right, these all have to be post-flood layers. These couldn't have been made during the flood, because all of them are sitting on top of sediments that are themselves, most young earth creationists think, are post-flood layers, like the Miocene layers, which are below all this basin, right? There's climate fluctuations. Lake Lisan records a bunch of different climate fluctuations over tens of thousands of years. I didn't go into the details on this. You can read the paper that is associated with this particular episode. And there I talk about the pollen record more. I talk about other evidences of the climate having changed. But the whole idea that the lake was way high and then came back down lower and then way, way up again, the only way really to explain that is the climate changed dramatically. Right? The whole pattern of climate must have been different over this region and changed. It's a cyclical thing. It's not like it was just one thing and it's gotten dry. It's gotten dry, it's gotten wetter. It's gotten dry, it's gotten wetter. That's not consistent with this single catastrophic flood event. There's a correlation of the climate changes we actually see in the sediment record with other places on Earth. So you go to ice cores in Greenland and you date the ice cores and you see things called Heinrich events. And you see places where we see like, oh, the Earth seems to have been much colder at this period and much warmer at these different periods. And the dates there match the dates of like, when we think that the Earth was colder, we see Lake Lisan as higher. Why? During the Ice Age, because the climate had changed, brought more precipitation to this particular area, also less evaporation. That causes the lake water to rise, right? When we have evidence of warmer periods, like, 80,000 years ago, then we find that the lake was much lower. And so that consistency of evidence from multiple places on the Earth also gives us reason to think that these are good records of climate change in the past. There's pollen records, and the pollen records suggest there's been a change in the ecosystem in this area. Like the different kinds of plants and animals, well, mostly plants, all right? The vegetation has changed quite a bit over times. And it's fluctuated in terms of like, here was a bunch of vegetation, and then it was replaced by a forest up on the mountains. And then the forest disappeared, and now you had grasslands, right? And other types of plants that are associated with deserts. And then you had forests, right? And guess what? When there's forest, it seems like the water was much higher. Well, maybe that's because there was a lot more rain, a lot more precipitation in the area, and so a lot more vegetation. And so those records also match too. And it also suggests that it wasn't just like a forest at one time and now it's a desert. No, it was a forest, then it was a desert, then it was a forest, then it was a desert, then it was a forest, and then there was a desert. Each of those transitions takes time. It's not like you have one year and one the next year. It's more like hundreds of years, thousands of years, tens of thousands of years to transition from one of those different stages to another. We have Lake Lisan. We have the Sedum Marsh. We have the connection with the Mediterranean Sea. Right? When did that happen? In the young Earth, the flood geology. Right? The geochemical evidence. I didn't talk about that, but we have trace isotopes, all right, and trace elements. So there are different elements that precipitate out at different salinity levels in the lake. And so as you look at those profiles, that's another thing you can use to interpret like the amount of salt that was in the water. And those change over time too. And it also tells you something about climate change. I mean, all these things are connected. Paleo-environmental reconstruction. Well, that's similar to you take the pollen, you figure out, that's what I just talked about. You can see that there's not some kind of instantaneous, like over a few decades, because that's what young Earth creationists need. They're going to have to say like this whole area was, forested, and then just a few decades later it was a desert. Shorelines. There are ancient shorelines stacked up on the sides of the Jordan Valley. Right, we'll look at those in the next episode. That seems like pretty good evidence that there were lakes there. And each of those shorelines represents some period of time. You don't just get a shoreline from it being there for a month or a year, right? These are shorelines in which they've etched their way and eroded into rock in some cases on the sides of the mountain. All right, so we're talking about potentially hundreds, thousands of years of the lake being at a similar level, allowing it to develop a very distinct erosional bathtub layer, before it then changes. Right. Oh, I just mentioned ice core records. We have really thick deposits of salt and gypsum, 6,000 feet of salt, gypsum, several thousand feet of that. How does that fit into young Earth creationism? How did that get made? How did that get made, like not during a global flood? I mean, even how would it get made during a global flood? I don't know. All right. I know young Earth creationists have some wild ideas about that. Some hypotheses, we'll call them. But this lake seems to have formed after the flood, right? The rift seems to have formed after the flood. And therefore, all the things that are in the rift, the 15,000 feet of sediment that's in the rift, has to have come from somewhere within a very short period of time, namely less than 500 years. So how might young Earth creationists respond? Well, they could say that maybe this lake I've been talking about, maybe it just formed rapidly, immediately as an aftermath of the global flood. Here's a natural argument. You can say like, hey, if there was a global flood, at the end of the global flood, this land broke apart. And maybe there is rapid tectonics, which is another one that's coming up here. Maybe the plates slid apart within the space of a couple of weeks or a month. They opened up, the land fell, and then there was a lake there. And that was Lake Lisan. And then over a period of several hundred years, Lake Lisan dried up, and that left us with the Dead Sea we have today. Well, if that's your argument, you can say like, okay, I'm going to show you that, that technically, I'm going to do the calculations. I'm going to show you could evaporate Lake Lisan down in just a few hundred years all the way to where it is today. You have to assume an extremely rapid environment, arid environment, and you have to assume like the Jordan River is basically almost cut off. But nonetheless, it can be done. But then you have the question of like how much salt would you leave behind? We're going to do that calculation. Maybe there was accelerated processes, like maybe just like the way things worked was different in the past. This is an argument that the basic laws, basically, of how sedimentation, precipitation work might have been different in the past than the present. I don't think many young creationists would go this direction, but if you get desperate, you might say like evaporites, maybe these are somehow accelerated processes that are basically miracles. You'd have to reinterpret the varves, right? You cannot acknowledge, young earth creationists cannot acknowledge the couplets are annual varves, that they represent years, because there's, in some sections, 10,000 of those which are countable in just one segment. And overall, 50, 60, 70,000 of them have been recorded. That represents 50, 60, 70,000 years in different places in the Jordan Valley. At most, you want to say that they can't represent more than maybe 300 or 400 years, right? Because you can only have varves occurring, between the time before Abraham and Lot visit the area, right? By the time they come to the area, Masada is like high and dry, and you have these huge mounds of sediments that are there, right? So there, you'd have to say they were all deposited super, super, super fast, and obviously not annually. They could say that the environment was radically changing. They could impose an ice age. Here's the problem with the ice age. Now, this is a really important point that I'll reiterate several times. If young earth creationists want to say that, oh, well, maybe Lake Lisan is the result of the ice age. The thing is, they propose that the ice age hit its height around 400 to 500 years after the flood. Right? They have a single ice age, which they admit the evidence for an ice age is so overwhelming that they have to squeeze in an ice age into Earth's history. So they say that after the flood, the waters are really warm because, of course, the oceans were almost boiling due to all the volcanic activity. Plus, the plates are all moving really fast, creating a lot of friction and therefore creating a ton of heat. So the environment was really, really warm. So the oceans were evaporating tons of water. That water then is going up and then falling in northern climates and turning into snow. And then the ice age is forming. So over several hundred years, the ice is forming. The thing is that the ice forms, and that means the Mediterranean Sea is much, much lower than it is today. But ironically, it also means that for there to be a large lake, Lake Lisan, right, during that time, you had to have more precipitation in this area. Right. Well, if the ice age caused more precipitation, you're like, great, I just solved that fits the young earth creationist model. The thing is, if there was a lot more precipitation 400 or 500 years after the flood, then there would be a large lake there. But the Bible tells us there was not a large lake there. Abraham and Lot, they tell us there's no large lake down there. Right. So, the ice age becomes a problem for young earth creationists. They have to say this is an extreme desert. Like right after the flood, this whole area must have been extremely arid. Why? Because you had to dry up that giant lake that was filling up there. Because if you had a giant flood that covered the whole world and cracked open, you have a giant valley, well, it's going to fill with water from the last remnants of the flood, right? So then you have to dry the whole thing down. How are you going to dry it down? You got to have no precipitation. You can't have it be raining all the time. And you got to have it be super dry in the air so that the water will evaporate. At the same time, young creationists are running around saying, well, the Sahara Desert was green and that was lush. And besides, they can see that there is evidence that the Middle East was much, much wetter in the past. If it was wetter, there would be a giant lake there, though. Now, conventionally, this is not a problem. Because you say 25,000 years ago, there was a large lake, right? And that's when the Sahara was green as well, right? And so, yes, it's been much drier for the last 10,000 years, and that would explain why everything's dried up. Some more things. Of course, you're going to have to question the radiometric dating. You can't say that this is 70,000 years ago, or that the Sedum Lagoon was 3 to 5 million years ago. They have to propose there is rapid tectonic activity. This whole thing split open, and the basin fell in, and all these rifts formed within the space of years or maybe decades. And that, of course, creates the heat problem, which I talked about in the last episode, where literally, like, you might melt the mantle more if you did that. And then you have to reinterpret fossils and artifacts. Oh, we're going to get to that. We're going to talk about artifacts and fossils that are found in layers of sediments in the Dead Sea Rift. I mean, there were villages, there's towns, there's cities that are like 1,000 feet below sea level. If there was a big lake, right, not long after the flood, you couldn't have made a city. You couldn't have made Jericho. Jericho's considered one of the oldest, cities in the world. Right? People had to gather there, had to have been above sea level for long enough to think this might be a good place to like build a city and build it and not have it covered with water again, which means no large lake has formed since Jericho was first formed. All right. First built. Yeah. This whole point of the whole series is we have to align this with biblical accounts, biblical eyewitness reports, which I agree with Ken Ham. The Bible is a true and faithful witness to these events, to these places. And so therefore can't be making up like, some giant lake that was around like 3,000 years ago that deposited all kinds of sediments in this area. So you've got, they also say, well, how did the lake disappear? Well, maybe there was catastrophic drainage. Drainage into what? I mean, there's a few young earth creationists that might say like, well, maybe there's caverns below the earth that were, that had somehow, when they emptied their waters to begin the flood, now there was sort of empty spaces, and maybe the water literally drained out through a hole at the bottom of the Dead Sea and filled the cavern up. I know that's a wild speculative hypothesis, but you got to come up with something to explain, where did the water from Lake Lisan go? How did it disappear? Maybe there's different water sources, right? Maybe water came in through what we are going to see. There are natural springs in the area, and we'll talk a little bit about how that water gets into the Dead Sea Basin. Right. So we have to note that all these hypotheses, each one faces really significant scientific challenges. Right. But what's, to me, the most powerful thing about this whole example of looking at the origins of the Dead Sea is it is a multitude of problems. And many different observations all point to an ancient Earth. Right. The data fits together really well if you have a lot of time. All right. Well, I'd love to keep going on this. It seems like there's so much more that could be said, but I've hit the highlights here. Again, I have my article, which sort of goes into more detail, but I also have to hold off because we're going to talk about a little bit more about Lake Lisan. All right. And that's going to be in the Dead Sea Chronicles part 5, right? The next part, Lake Lisan's legacy, what stromatolites reveal about Earth's past. And we'll take a look at some specifics, right? We'll go to a couple papers and we'll look at some specific data that will help us establish how they figure out the dates of these shorelines and why I'm so confident that these shorelines represent hundreds and thousands of years of time for each of these different separate wave-cut benches on the sides of the mountains. That's, again, you just saw, that's an incredible challenge to young Earth creationism, since they need to get rid of this lake that was in this Jordan Valley within the space of a couple hundred years. There's no time to have lakes just pausing and hanging out for thousands of years in order to allow stromatolites to grow on the shore. So there you go. That's what we got coming up next. Thanks for hanging out with me. I really appreciate it. We'll see you next time. Thank you for watching this installment of the Dead Sea Chronology series. As we've explored today, the Dead Sea region provides fascinating insights into Earth's history and raises important questions about how we interpret both scientific evidence and scripture. If you'd like to dive deeper into this topic, I invite you to visit my blog, Naturalis Historia, at thenaturalhistorian.com, where you'll find detailed articles exploring each aspect we've covered today, including full references and additional resources. Here's the schedule for upcoming episodes in this series. Each new video builds on what we've learned today. helping us better understand how geology and questions of the Earth's and our origins intersect in this remarkable region. You can learn more about my work and background at joelduff.org. If you found this content helpful, please consider subscribing and sharing with others who might be interested in exploring these important questions about science and faith. Thank you again for watching. Blessings to you and all who are around you.